So that's the first thing. So we can clear all this out. Now, once again, we have exactly as many zero modes as integrals, so we get something non-zero. But from each of the brackets, we have to choose a different zero mode insertion. Right? Because you have to have, the only way to get something non-zero is having one product of each zero. Is that clear? Right? If you choose, well, it's even simpler. If you chose the same zero mode insertion twice, the term is just zero. It's that symmetry. Okay?
But the Grassmann nature.
Because the Grassmann nature of the variables. Right? So the only way you get something non-zero is choosing a different zero mode. But you can choose, there's play involved. You could choose the nth zero mode from here, the nth one from there, and so on. There are many possible ways in which you can do this choosing. Each possible way will give you an answer. Now, there's a leap of imagination I want you to take. You can check this for 2 cross 2. Can somebody guess what the answer to this? What the answer to this path integral is? So suppose we chose the first zero mode from here, the second one from here, the third one from here, the fourth one from here. What will we get? We get the product of all these factors, where this one was replaced by B01, this one was replaced. So we would get a factor like B01 del 1G times B02 del 2G, and so on. But now suppose we chose instead the second zero mode from here, the first zero mode from here, and everything else the same. Then what will we get? We get B02 del 1G, B01 del 2G times the same stuff from here, but we'll also get a minus sign because we've done the integral of things in different orders, and so on. We get many such terms. Now, can somebody guess what we're going to get? Actually, if there are only 2 insertions, this is the full answer. What is this? Say it loudly. Determinant. Exactly. So let's define the matrix MKK prime as equals B0K del K prime G. This path integral is the determinant of that matrix. It's proportional. Is this clear? Right, this is a set of numbers. These are the zero modes. You take the inner product of this thing. There are m of these. It's an n cross n matrix. Take its determinant, and that's the answer. Fine. So the net result of doing the zero mode integral over B, including the B insertions, the net result of that is a factor of determinant of B0K del K prime G. Let's also quickly look at what you get with the C's. Okay? What you get with the C's is also equally simple. Remember what we had? Let's look only at the leftovers. With C sigma I product over I. Okay? Now we're doing zero mode expansion. So somebody tell me what we're going to get. Only the zero modes. And what's the final answer going to be? Determinant of something. What should I put into something? You see, what's different about these different insertions, different points? At each of the different points, you pick up a particular different 0. You know that. So this is now again a V cross P matrix with the indices being which 0 and which point. Okay? So this is what you get. This is the result of doing the path integral over the 0 modes of C, including the contribution from the insertions. And finally, what do you get in the path integral that we looked at by doing the integral over all the other stuff? They're not zeros. Well, that was just some overall factor. See, because none of the insertions now depend on B and C anymore. Okay? So that's just an overall factor, some determinant, it's product of gammas which you can regulate in some way. Throw it out. It's gone. So the whole result of doing the ghost path integral is these two determinants. All that remains is to do the matter path. Okay? So this ghost path integral, blah blah blah. One way of thinking of it is that it's just a convenient way to derive these two determinants. Once you have these determinants, no more ghosts. Okay? Now this will not always be the most convenient way to calculate. Sometimes easier to actually evaluate the ghost path integral than calculate a determinant. But you should remember that this is an alternative. Okay. Now, we started this discussion by saying that we wanted to show that the measure that this integral over moduli space was invariant under field redefinition of moduli space. Now it's obvious that this is the case. Somebody can give me the argument. Okay, yeah, sort of, but it's similar than that. It's easy. It's dmp times, the only thing that depends on p is this thing, right? Times determinant of bk0 del k prime g. Now suppose we make some transformation, some field gradient. T is equal to Ta is equal to fa of t theta. How does this major factor change? It's the Jacobian. Determinant of the Jacobian matrix. How does this determinant change? By the inverse of that determinant of Jacobian matrix. You see, because this matrix picks up a product of the inverse Jacobian, and then you use the fact that the determinant of products of matrices is the product of determinants. Okay? So this measure with this insertion is invariant under coordinate redefinitions. Okay? So the question of what measure do we use in the space of moduli is not important. You can use any measure you want to get the same answer. I should say that the different measures have to be related by one-to-one transformations. Because some subtlety here. In changing measure, you get an absolute value, and here you don't get that absolute value. So if you don't make it one-to-one, you'll run into problems. But of course, you do want to make it one-to-one because you want your coordinates to be a faithful set of coordinates on moduli space. So if you started with a faithful set of coordinates on moduli space, it will only remain faithful if it's one-to-one. So that's not visible. Okay, so once you have a reasonable parametrization of moduli space, you've got your answer doesn't matter. It's just here. Okay, this is our first nice payoff. We've seen that a possible Y you might have had is not a Y. Okay, great. So we've understood the variation under change of model. I'll let you guys go and find it. Just very quickly, 2-3 more things. Okay. We will have class next Friday as far as I know. Okay. And yes. Okay. So now, questions, comments, or we go on to the next one?
directly, looking at the Fadi determinant. After we got the ghost they did something and then we integrated the ghost again.
Yeah, you see, if our original procedure had been completely consistent, we were guaranteed that all these properties are true. Because if we did everything correctly, we've got a sensible answer. But this is now a check on the answer. In the end, there are a lot of formal manipulations that go on when you do this derivation. And you might. So I think a sensible approach to take is to treat that derivation as heuristic, but check the answer for every property that is of physical importance. So that's what we do. So in some way, there is a formal argument starting from our procedure that tells us it has to be true. But this is what we just by explicit evaluation showing that it is true. That's the spirit of what we do.
No, do the explicit evaluation of the Fadi Papo itself.
Okay, that's a huge. It sounds like a huge infinite dimensional matrix. Yeah. What do you mean?
Okay. For example, these determinants are basically Fadi Papo because which we exponentiated into those.
Right. Yeah, but you see what we've done here is thrown out the part that there was an infinite dimensional determinant. What we managed to do very nicely is separate the part that doesn't matter and the part that plays with the moduli. So that's what we've done. Taken the Fadi-Popa determinant, shown that it does depend on the moduli in a very simple way. In a way that cancels the change of measure.
Only the 0 point.
Exactly. Okay, good. So that's the first property we were interested in. Now, there are many other things we should check. About, some of which have been running Jyotin, I think. Okay, so the next thing, I'm just going in order of Kulchinsky, all the things he checks. Okay, so the next thing you might want to check is, how do we know that the final answer does not depend on what fiducial metric you've used? You used in your construction suite. Suppose we take two different metrics that are related by Weil transformations, will we get the same answer?
This is
Welsh metric, right? Okay. Now you might be thinking, well, and this sounds like deja vu. We've been through this before. We went through this whole discussion of how the trace of the stress tensor and therefore the partition function and so on didn't depend on the Weil factor, provided we put the critical dimensions. It's a question. And you're completely right. If we were just doing the integral of a partition function, we know that it doesn't depend on the Weil factor. But we're not just doing the integral of the partition function. We also have these various insertions. Okay? So we should make sure that that our insertions are all also Weil. Okay. Now this is a very easy job. It's a very easy job because it's a very easy job because remember that B and C were themselves Weil. You remember that when we wrote down the action, we saw that we chose the right index structure for B and C. They were Weil independent fields. Now these physical vertex operators have these insertions of V have definite Weil transformation properties. Okay, they have definite Weil transformation properties. In fact, the same Weil transformation property as the inverse of the metric, because they're 1-1 operators. How can we see that? You see a conformal transformation. These operators are Lorentz scalars. They have no spin. It's a conformal transformation. Okay, a conformal transformation is some compound of a Weil transformation and some diffeomorphism. Okay, so if we understand how these things transform under, we know what the transformation is under conformal transformations, and we know what the transformation is under Weil transformation, under diffeomorphisms, then we know what the transformation is under a Weil transformation. Okay? But these things are essentially diffeomorphism scalars. So all of the conformal transformation properties come from Weil transformations. And we've seen that the operators, these V operators, have to be 1-1 operators. How have we seen that? We've seen that because we know that the corresponding state has to have L0 equals 1 and L0 bar equals 1. And under the state operator map, that maps the scaling direction of the operators. Okay? We've also seen that these operators are primary. That's crucial. We've seen that they're primary, therefore their transformation under conformal transformations is very simple. It's just del z by del z prime to the power 1, del z tilde by del z prime tilde to the power 1. And now, if you convert that to a Weyl transformation, it's exactly the Weyl transformation of an object which, like the inverse of the metric. I've said this fast, but is it clear? Yes. If somebody wants, well, maybe we play. Okay, well, is this clear? Somebody wants me to go through this in more detail. We could have a little fight. I could write this in formulas next class. Maybe I should. I'll do that. I'll do that. But is it clear? Is the idea clear? There's no need ever. Let's say this formula like this. You remember when we were discussing conformal field theory long ago, we discussed the transformation of primary operators under conformal transformations. Okay? And we said that if an operator has weight h bar, then the transformation has the part h del z bar del z bar prime bar h bar. This is the factor of transformation. Okay, but now let's compare this to the metric. How does the metric transform? Well, yeah, 1 minus 1 depending on your conventions, right? Okay, so the metric or the inverse of the metric, we have to get our convention straight, will transform exactly the same way, but with factor 1 and 1. Okay, so this conformal transformation is exactly the same as that of the metric. Oh, let me say this better. You see, under the same coordinate change, the metric transforms by a Weyl transformation. The metric transforms by a Weyl transformation, and the Weyl transformation factor is this, with either 1, 1 or minus 1, which I get straight if we were doing it directly. Okay? So this thing is exactly the factor of the Weyl transformation. If the primary field under question is 1, 1. Okay? So what we're saying is that now if you did it correctly, I would have to get either the inverse is correct. But if g alpha beta goes to e to the power minus 2 phi g alpha beta, then v goes to e to the power 2 phi v. If the operator v was 1, 1. You see, it's either this with one of the two signs. You can see that immediately, right? It's a matter of working out the signs. I assure you that this is the right answer. Okay? Because of that, every insertion of square root g times v is Weyl neutral. Okay, so this part of the insertion is fine. B and C is fine. Actually, there's only one thing that is dangerous, and that's the B insertion. Let me remind you. Is it B insertion? And let's write it out in detail. The B insertion was square root g alpha mu, g beta nu, del alpha. It was B alpha beta del k g mu. Okay. Now suppose we form a Weyl transformation of this. First, let's count weights. There are as many square root. You see, this is weight. Suppose this transforms like e to the power minus 2 5. This transforms like e to the 2 5. This transforms like e to the 2 5. This transforms like e to the power minus 2. Okay? So this looks okay. It's all cancelling. Except that this del k can act on phi.
Phi depends on the modulus.
You could choose it to depend on the modulus. It shouldn't matter. You see, because the moduli are a choice of fields. You see, well, G here is a choice of fiducial metric. It's a choice of fiducial metric for every choice of modulus. And if you choose a different choice of fiducial metric in a modulus dependent fashion, that's okay. Right? Your answer should depend on it. Okay? But that's actually not a problem because, you see, B is traceless. So if this del k acts on this 2 phi, it contracts B with G and you just get 0. Okay? So this potential problem in this insertion is also not there. Okay? So Y invariance I'm claiming is manifest. It's manifest in the action because the stress tensor is traceless in the critical dimension. It's manifest for C insertions because C is wide invariant. It's manifest for square root G times V because V is a 1-1 operator. It's manifest for this thing because the only potential problem is 1. Okay, so our path integral is actually completely wide invariant in the sense that if you choose different fiducial metrics that are different from each other by some wild transformation, doesn't matter. Okay. Should I talk about? Okay, let's do next. Should I? Well, you guys science host. Let's do it. Okay, I wanted to tell you about DRST invariance, also about diffeomorphism invariance. You know, we've got these things inserted at specific points. Okay, that's very funny. If I choose different points to insert these things on, will I get the same answer? We want to prove that. We want to prove that the action that if you change the vertex operator by vertex operator.